We can also compute the distance from Bill and Julie. So if I'm looking at Julie, right? Here's Julie. She's on my phobia, right? So she's there in the middle, and then and of course it's on the same spots because she's in my horopter. I'm focused on her right there and there. But Bill's closer to me, so his spot on this side is going to be here, and on this side it's going to be here. Now, if Bill's corresponding spot was here, that would mean that he was in the same horopter as Julie. He'd be next to Julie. But in fact, Bill appears on the other eye here. So we compute that absolute disparity, and we're able to tell how far away Bill is from Julie. And similarly here, if we're looking at Bill now, right? If we look at Bill, he's in our horopter, and Julie's behind the horopter, this new horopter, right? So Bill is on our fovea, so he's dead center. But Julie's not in the horopter, so on this eye she's here, and on this eye she's here. So the corresponding point for the other eyeball is here, so we compute that disparity, and we're able to tell how far behind Julie is from Bill. So the depth information that's provided by this disparity, by measuring the disparity between the left eye and the right eye, is called stereopsis. That's the information that we get. A stereoscope uses two pictures from slightly different viewpoints. I don't know, back when I was a kid, they had these little viewfinder things where you would put a little round thing with pictures in it into a machine and click through the pictures, and then you would and it would look and it was in 3D, and the reason it was in 3D is because you were looking at two pictures at the same time, and they were slightly different. Another way to get this illusion of 3D is to use what's called a Randomdots stereogram. It's a really neat experiment. Let's see if I have a picture of it here. Well, I don't. But anyway, a Randomdots stereogram is where you have random dots on a picture, and then what you do is you take a little square of those random dots in the picture and move them over one bit or one pixel, I guess, right? Move just a little square out of that picture, move over one pixel, and then you project the original picture to one eye and the one with the shifted over dots on the other eye. And when you do that, you actually see the little shifted over dots floating above the picture like in 3D. So once again, we use this perception of depth, this computation of disparity, the relative distances between these trees, for example, how far away they are from each other, to compute the perception of depth. Here we have an example of a stereograph, right? And what this is two slightly different images. Basically, what they did was they took a picture, and then they walked a few steps off. It looks to me to the left. They walked a few steps to the left, and then they took the exact same picture again, another picture. And then you take those two pictures and project them one to each eye, and what you should get is this three-dimensional effect. I've actually tried this, doing this, building a little stereoscope, and it works really well. There are the technology now for three-dimensional television creates this stereopsis. In other words, creates this giving images to different images to one eye versus the other eye in a number of different ways. One of the ways, the simplest, cheapest way that it's done is through passive polarized glasses. So basically, what you have is you have two on the film. You have two images laid on top of each other. One that is just slightly off from the other. And then you have special glasses that are polarized. So in other words, the glasses only allow light that is coming in one direction hit your eyes, and the glasses are shifted so that light coming in one direction goes in this eye, and light coming in one direction goes into the other eye. And that polarized light, the differences in the polarized light between eyes, gives you that stereopsis, that those different views on your retina, and it gives you the illusion of 3D. Active 3D is what's used mostly in the movie theaters and as well as on 3D TV. And what they give you these electronic shutter glasses, and basically what these glasses do is they flicker on and off at different rates to give you a different perspective on this eye and a different perspective on this eye. And then finally, there's the most expensive 3D TV technology is lenticular technology. And this is where the screen actually has little tiny lenses on it. And the lenses take each point on the screen and produce a slightly different image out of each lens. And then your eyes see those based on the angle that you're at. Your eyes see those two images, but it links them together in your brain to create, and ultimately creates this three-dimensional image. So here's an example, right? Polarized images, where the images are just made with two different light patterns. Rapidly alternating images with the electronic shutter glasses that are synced to the television. That's what's used in the movie theaters. And then finally, the mini lenses on the screen, where you don't have to wear glasses. There's lenses on the screen that quickly present you with two images and allow you to get this three-dimensional effect. Oh, here's the stereogram right here. So basically, you can't really tell by looking, but these two are different. This is a random pattern of dots. Random pattern is of ones and zeros. Wherever there's a 1, it's dark, and wherever there's a 0, it's light or white. And you can't really tell because it's a small square. But what they did, and these are stereograms, is represented here in this image here. So what here's the random pattern of dark and light squares, and here's the little square that I'm going to shift. So I identify these little squares, which are indicated with A's and B's. So A is black and B is white, and then I just move them over one by one pixel. And then I have to fill in the blank, so I just fill it in with some more random dots. So Y is white and X is black. So I end up with pretty much the same image as here, except that these squares here have been shifted over by 1, and they're the same squares. Notice that it's the same patterns, A, B, 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 A, B, A, B, blah, blah. They're all the same. It's just been shifted over by 1 pixel. And when you project this image to one eye and this image to the other eye, you will see this little square here, which is here somewhere, I guess. This little square here appear as like it's floating above the bigger square. So one of the big problems we have with figuring out how our eyes work is known as the correspondence problem. And here's the correspondence problem. How the heck does our visual system match the images from the two eyes? Because if you think about it, if you're looking at something, if you think about it, the images from both eyes are different. Especially if you're looking at things that are not in the same horopters or whatever. I mean, the images are different. So somewhere along the path of computing your visual perception, there has to be a process where the image from this eye is somehow connected or linked to the image from this eye. The reason the random dot stereogram experiment was so important was because people thought one of the theories for correspondence was that, well, we're using, we know what objects look like. So we're using corresponding points in an object to link them together. So, if you're looking at this pen, right, you know what a pen looks like. And, this is being projected onto the retina of one eye, and it's being projected to the retina of the other eye. And your brain's just going to say, oh, that looks the same in this eye and that eye. I'm going to call that one thing, right? But you can't say that with the random dot stereogram because it's just a random pattern of dots. So that's obviously not what we do. So we don't know, we don't have an answer to this problem, basically. We don't know how it is that our brains create one unified view, one unified three-dimensional view from two eyes. We have no idea. So let's get a little bit now into the physiology of how some of this might work. So we have identified neurons in the visual cortex that fire best, that respond best to binocular disparity. So when we're projecting, looking at something that's very close to us, that's not in our horopter, in a particular horopter, and there's that great binocular disparity, we have been able to identify cells that fire. And these cells have been referred to as binocular depth cells or disparity selective cells. And what's really interesting is that there are cells that respond to specific degrees of absolute disparity. There's cells that will respond when the disparity is very great. And then there's other cells that will respond when the disparity is not so great. And you can actually find a cell, measure its output, its firing rate, and then present different images onto the retinas with different sorry about that. Present different images to the retinas and measure how much disparity each cell responds to. So, for example, here's one cell, right? We found one cell, and with a 1 degree disparity, minus 1 degree disparity, there's no firing at all. Once the disparity is 0, there's quite a bit of firing, but the best firing occurs when the disparity is 1 degree plus, when it's 1 degree over to the other side. And then it falls off as you get away from that. So in this example, in this particular fake data, we found one cell in the visual cortex that fires best when the binocular disparity is about 1 degree, which isn't that far, which isn't that much, by the way. So we saw this picture before. I think in the first chapter, and it represents this relationship between the stimuli that are out in the real world, that impinge upon our senses, the physiology, which is all the neurochemistry and neuroanatomy responsible for us perceiving things, and then the actual experience of perception. So the stimuli, the relationship between the stimuli and perception is that we know that binocular disparity causes the perception of depth, stereopsis. So the greater the disparity, we use changes in binocular disparity, where those relative points are on each retina, to compute a perception of depth. We know that. the relationship between the stimuli and the physiology, we've, as I showed you just now, we have found neurons that respond to differences in selective differences in binocular disparity. And then finally, the relationship between the physiology and perception. We can actually eliminate greatly reduce the number of disparity selective neurons by raising test animals in situations where they have no depth to look at, where everything's just flat. So if you raise mice or rats in an environment where everything is flat and there's no depth, they will not develop these. They will have greatly underdeveloped neurons that detect binocular disparity, and that will affect their depth perception. They will not be able to perceive depth as well as normally reared animals.